Okay, good morning everyone. So before we start, I just wanted to show a very quick feature in VS Code that was going to make sure that you work in the correct folder. So like in this specific example, I am working on in a folder called MDL1, which is stored somewhere in my computer. And one thing that is very important when you are starting to work on your project, when you show VS Code welcome screen, is the start option here. And the start option is going to let you either create a new file or open a folder. So when you open a folder, it's going to bring you to your system's folder dialog, and then you can pick one of the things that you want to open. What this is going to do is make sure in your terminal here that you are working within the correct place. So if you need to compile the report for the project, it's going to work if you are working from within this specific place. If you just start VS Code and you're not in the correct folder, it's not going to work. So just make sure that you are working in the correct folder at all time. I'm just going to pick the one for this class. Another thing you can do is when you are working on a Julia project, you can right click on any file. And in the menu here, go to change to this directory. And this is going to bring you to the correct directory. So that is one way of making sure that you also working in the right place. When you're running some Julia code, you could also use the command pwd, and pwd is it's shorthand for print working directory. So tell me where in my computer I am working, and we are working here in /home/my username /work/teaching /class name the specific project. So you can make sure that you are working in the correct place. You can also, by the way, you can also check that we are working in the correct environment, because it says when we go into the package mode, it says MDL1, which is the name of this folder/project. And we can see that we have installed 2 of the packages that we will need for this module. So whenever you have an issue with being unable to save your plot, or you are running a file and say another file is not found, it is most likely because you are not actually working in the correct directory where the files should be. And the first step is like check that it's the correct directory, check that the package is activated. And if that's not the case, then you have a different problem, reach out to me and we will we'll find out what it is. All right, let me just make the code slightly bigger. 14, it's good. Yeah, okay. So today we are going to do one of my favorite things, which is we're going to do some analysis of a model without having to do much mathematics, or almost any mathematics. And the reason we can do that is because we are going to look at visual techniques that can let us look at the equilibrium points in a system. So you've read the different chapters of our textbook, and you know that an equilibrium in a system is defined at a point at which the variables are not changing anymore. So if you have a population density, and when you reach a certain population density, the system stops moving, and that point is an equilibrium. And there is a way to identify them mathematically. There are several such ways, in fact, but there are also ways to identify them very visually. So what we're going to do during the first 45 minutes is look at one way to deal with single variable continuous time systems. And we're going to look at using a very simple plot to identify where the equilibriums are, and then make some inference about what the system behavior should be around these points. In terms of the mathematical notion that we need, we will need to talk a little bit about ordinary differential equations, and we will see different types of differential equations during this class. We will see partial differential equation. We'll definitely see some stochastic differential equation, and we will maybe almost surely have time to talk about Bayesian differential equations. Because if there's one thing I like, it's just adding layers of notions on top of one another. So we'll start with the very simple ordinary differential equations, which I may realize are not so simple because I am also a biologist and I'm still somewhat terrified of mathematics. I think it's a healthy feeling to have. So let's discuss what a differential equation is. Before we do that, let's start with a simple, very concrete example. We are going to write a logistic growth model because it's all we need to do. Like, we can teach an entire graduate class on modeling based on this model alone. So the logistic growth model takes a variable n, which is a population size. Let's do that. So the variable is n, and it's a population size. And we have some parameters, which are r, the growth rates. And we're going to call it alpha, which is the intraspecific competition rate. And that's it. So we have one variable. There's a single population that we are tracking through time. And we have two parameters, a growth rate and a rate of intraspecific competition. The difference between a variable and a parameter, they're explained in the book. A variable is something that changes over time and that we are interested in tracking. A parameter is something that can also change over time, but it's more something that is external and that is driving the behavior of our variable. So, to write the equation for this logistic growth model, what we would say is that I'm just going to write the mathematical notation. dn over dt is going to be nr minus alpha n squared. That's you may also have seen a version that is r minus nr times 1 minus n over k. That is the same thing if we assume that, that's what we're going to do, actually, that alpha is 1 over k. So that's a different way of expressing the same model. So either we express it as a carrying capacity, we know how many individuals at most can be in the population, or we express it as a rate. We know how strong the competition between two individuals are. If you pick alpha equal 1 over k, and if you run the two models, they are going to be giving you exactly the same dynamic because they are exactly the same model. That's a first, actually quite deep insight about modeling, is that you can express the same mechanisms in different ways. If you know something about the carrying capacity, you can write a carrying capacity model. But the carrying capacity gives you an information about the strength of competition because 1 over carrying capacity is intraspecific competition. So never mind that. We are going to use this model here. So what it means is, once again, explained in the textbook, but it's basically a way of saying that for every very small change in time, so when you move from t equals 0 to t equals 0 plus something very, 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 very small, you will see a change in the value of n. And the value of n that you will see, I have no idea why my text editor insists on this equation being green. That is apparently the official color of the logistic model for now. I'm fine with that. So when you have a very small change in t, you will see a very small change in n, whose value is nr minus alpha n squared. Why are we expressing this? Why are we expressing it this way and not in a and not in a way that is a function of n over time? It's because for most models, we do not know the expression of n over time. So this function n over t is, in the majority of models, something that we don't know to express, because we don't know exactly what the mechanisms are, and because we don't know its shape. In the case of the logistic model, we know it. We can take the antiderivative of this expression, and that gives you a curve that is called a logistic curve, and we could do n over t equals something that we can write down. For many models, we can't. There's also a more pragmatic reason, which is in a lot of situations, it's easier to think about what makes a population change. And so a model based on differential equation is a model that is expressed in terms of mechanisms. And in this model, we have two mechanisms. We have mechanism 1, and its growth, and it's n times r. And what it is saying is, well, every proportion, every individual, every component in this population is going to grow with a rate that is r. And then we have mechanism 2, and mechanism 2 is competition. I'm just going to put arrows in here, so that's going to be easier to read. Mechanism 2 is the rate of competition is alpha times n squared. So that means that when you have one individual and it encounters another individual, that's why you have a square here, they are going to compete. They're going to have an interference between one another at a rate which is alpha. So that are ecological mechanisms that we can think about. And so we can put that into a differential equations. So let's write a function to do that. So we will have a function that we will call logistic. And this function needs arguments that are going to be n, which is the population size, r, which is the growth rate, and alpha, which is a competition rate. And it is going to return n times r minus alpha times n times n. So this function is a function to give us the time derivative of n. We can do a bunch of things with this function, but we're going to do a first quick little, take a quick little detour in a programming concept that I think is fairly interesting. So let's say we want to do a bunch of simulations of this function. I don't know why. I have no idea why. Let me remove this line, which seems to be, I don't know. Okay, anyway. That's very annoying. We can do a bunch of things to this function, but we might want to get rid of the parameters for the moment. So we don't want to have to specify the value of r and the value of alpha. One of the mechanisms that we have seen to do that is to declare these as keyword arguments and give them a default value. That's a thing we can do. But there's another little trick. Another little trick we can do, which is function. A very good question in the chat. What are the units of alpha? I love this question. So, yes, what are the units of alpha? That's a discussion I usually have in what are the units of the parameters? That's a discussion I usually have in a class a bit later, but let's go with that. So what we're modeling is dn over dt, which is a change of individuals over a change of time. So we know that we have a first mechanism, which is growth, and growth is expressed as population times a rate. And so what we know is that a rate is something that is something over time. So it's a population over time. What are the units of alpha? Well, the units of alpha are going to be the same. Like, so sorry, the unit of alpha times n squared are going to be the same as that. So alpha is going to be defined as, and the units of alpha are going to be it's population minus 2. Is there a, I think I can do, yes, population minus 2 over time times a population squared. And that's population minus 1, sorry. Minus 1. So that's a good question to ask. It's going to be particularly important when we do modelings with actual number of individuals. For the moment, it's based on its frequencies, right? So it can be arbitrary. We can bound the value of n to be between 0 and 1, so we can change the dimension of the systems, but in some very specific cases, we will have units that are expressed in days or events per days or things like that. As a rule, it's always a good idea to check the units of your model. There is a discussion of that in Auto and Day with some techniques you can use, and the units must balance. So back to where we were. The little trick that we can do is I'm going to call that dn dt, just to be a little bit lazy, and we are going to write a function which is going to return a function. That's something that takes a little while to wrap your head around, but let me show you what's going on. We are going to write a function that is a function of r and alpha. So you'll see here that it's not a function of n at the moment, because what we want to do is return a function of n who is going to be the logistic of n, r, n, alpha. So at this point, you would be within your right to wonder why. What is the point of that? Well, the point of that is that it's going to be making a lot of manipulation much easier, because we're sort of taking the parameters we want and putting them into a function. So we don't need to think about the parameters anymore. They are part of the function. They exist within the function, but we only need to say, here is the value of n. So let's try. What if we do dn dt of one growth rate of 1 and a rate of competition of 2 times 0.02. That is a function. And if we apply this function to a population, it is going to tell us, well, the dn over dt, the derivative at this time, at this value, is 0.98. If we try with a very, very high value, it is going to tell us various things. Let me check that the model is correct. And minus, yes, okay. So what is happening here is that our, instead of having a single function with multiple parameters, we have a single function that is taking only the population size, and the parameters are built within this function. That's something that is fairly common in Julia. You can do that a lot because we can manipulate functions the way we manipulate any other concept. So we manipulate any other objects. Functions are variables with types, and we can return them, we can create them, and we can have functions that write functions. It's something that you see also in R very commonly. It's something that exists in most programming languages that we use in biology. but understanding how to use it is going to be important. So, and the reason we might want to do that is because remember that we can do a quick plot of a function. So let's say the model we use, we're going to call a model M. That's not necessarily a very good idea. The growth rate of this model is going to be 0.6, and the competition rate is going to be 0.1. So that is a function, and we could plot M. Remember that using the plot package, we can plot a function directly. And we are going to plot M between 0 and 2. I don't know. It's going to be taking a little while because, it's going to be taking a little while because I have not loaded the package. I'm going to do that now, and then we're going to re-execute this thing. I am loading a package called Zygot, and we will see in a minute what Zygot is doing. Essentially it's doing magic. It's doing math, so you don't have to. And we are very grateful for that. So let's wait until everything is loaded, and we are going to see our plot. So what this plot is going to show, while it's preparing to appear, it's time to take some time and think about that. Is going to tell us, as a function of the population density, what the change in the population is going to be. And so sometimes we'll see a change that is positive, sometimes we'll see a change that is negative, other times we will see a change that is 0. Let's have a look at what the plot is doing. Anytime now would be good. So the point of this the point of this plot is really going to be reading the behavior of the system. There's nothing that we will see here whenever we see it that is not something we can achieve on with some mathematics. All right, but it's also going to be much easier to read that. Okay, so I've done a plot between -10 and 10, and the first thing that we want to see is that it is intercepting 0 at some point. So let's do a quick let's do a small number of things. I'm going to be giving correct labels to this plot. So population size is here. Because we're dealing with population size, it doesn't really make any sense to have the population size be negative, because population size are going to be something that is at worst 0, the population is extinct, or at best something that is a positive number. So we don't need to go lower than that. Okay, so here's the population size, and then the y-axis is going to be the change in population size. So that's pretty cool, because what we have is times where the population is positive, the population change is positive, and the population times where the population change is going to be negative. Let's tweak our plot a little bit. We don't need to have a label because we know what this is. So this curve is the equation of dn over dt. What we care about is the points where it is going to be either positive or negative. So let's help us build a plot where we are going to highlight the 0 line. Okay, So that's better. Let's help us a little bit more by saying that we want to fill it up until 0 and then with some degree of transparency. Maybe a little less transparency. Perfect. Okay. So what do we have here? We have a plot that is divided in 2 areas. We have one area from 0 to some value here, and up to this value, it is going to be positive. So if you have a population size of 2, then you will see a growth that is positive. And so the growth means that the population is going to increase and shift to the right. So it's going to shift and shift and shift and shift up until the point where it stops shifting, because we reach a population size of 6. It's specifically 6 here, and you can work out why that is 6 based on the model, but we're not doing the mathematics here. We don't really care. We're just going to accept that it's 6. And then the growth rate is going to be 0. It means that whenever the population is exactly at this point, it is going to stop moving. If we had a population that was 8, then when the population is 8, we know that its growth rate is negative. And the fact that we have a negative growth rate means that the population is going to be moving towards the left. It is going to be decreasing. And it's going to be decreasing up until the point where it reaches n equals 6. So one thing that is interesting in this plot is that we can read it in a very visual way. Whenever the curve that gives the time derivative is above 0, the value of the variable is going to increase towards the right. Whenever the curve that gives the time derivative is below 0, it is going to move towards the left, and that means decreasing. And as a result, the point that is in between, so the points where the line is crossing the 0 axis, it's going to be an equilibrium. So if you take the function that gives the derivative and you just plot it, you look at all of the points where its value is 0, that is an equilibrium. We don't need to go as far as 6. Let's go up to 8. Okay. So there's one equilibrium that is 6 that we have talked about here. There's also another equilibrium here, which is the point where the population size is 0 and the change in population size is 0. And it's this little bit of Newtonian mechanics of population dynamics. The population with no individuals is not going to change in size. There is no population here. So unless you have a term like constant migration in your model, for example, then your population is going to keep staying where it is. So we have one equilibrium, which is usually called a trivial equilibrium, where there is no population and therefore the population is not growing. And we have one equilibrium, which is non-trivial, and it is an equilibrium for which we have reached the carrying capacity. So reading this sort of plot is very important because it's going to give you an intuition as to how many equilibrium you should expect. And as long as the curve that describes the time derivative is crossing the origin, so it's the 0 line, then you will find an equilibrium here. Next week, we'll talk about whether they are stable or not. But it's also going to tell you how fast the population is growing. The one thing that's interesting here is, let's take this point here, is the maximum growth rate of the population. So if you're interested in when is my population growing as fast as it possibly can, well, the point is the moment where this curve is peaking. There's another little trick you can do, and that's why we use Zygot. So Zygot is a program that does automatic differentiation. Because one way to describe, so the time derivative is describing the rate of change of the population size over time. And so if we take the derivative of that, so the second order derivative, d2n over dt2, it is going to tell us how fast the rate of change is changing. So think of it as the population is your position in space, the derivative is your speed, and the second order derivative is your acceleration. So we can describe the acceleration or deceleration of this population in using a little trick, which is to plot also the second order derivative. So to do that, when we use zygote, we can create a new function using this syntax called m prime. Because prime is what we use to note a derivative. And then when we run this command like m prime, you will see that the result is a function. So it's telling us that you give it a function, and then what zygote does is that it's going to create a function that describes the derivative of that, which is really cool because we don't have to calculate the derivative ourselves, even though here it is not that difficult. So we are going to give it the same limit. We are going to not have a label, and we are going to dot it, I would say. It's fine. So when we plot this second function, and it might take a little bit of time just to make sure that everything is calculated and everything, it's going to tell us when the rate of change is going to move from being increasing to being decreasing. So that's also an important information. And the main interpretation to make of that is the point where the second order derivative is going to cross the 0 line. It's going to be an inflection point. So let's give it a little bit of time to finish running. All right, here we go. Let's just fix the xlim for that. It's going to be 0 to 8. I'm going to put it here. Okay, so let's follow this line here. Well, it's telling us that up until from this point here, so population equals 0, to this point here, the rate of change of the derivative is positive. So the population is, we know the population is growing, but we also know that it is accelerating because the more, this value is positive, and so the change is itself changing positively. At this point, we are crossing 0, and then the second order derivatives become negative, and that means that the population the growth is slowing down, and it is slowing down up until the point where we reach 0. After that point, we don't really care what's going on because we're past the point where the system is going to get, in this case, back to its equilibrium. But that is useful to identify the fact that we have one maximum growth rate point, which is the point where the second order derivative is going to be 0. So that's a technique that you can use to identify minima and maxima in curves. But in this point, like plotting the second order derivative is going to tell us, here is the moment where your population is going to stop accelerating its growth. And so that is the point where the growth rate is maximized. That is an interesting information. For example, if you do things like growth rate of microbial populations, then you might be interested in what is the maximum growth rate that my bacterial culture is capable of achieving. And so if you have a model that describes the growth, or if you have a time series, and you get a second order derivative, you can get this point this way. So that is something that requires no mathematics. We didn't even have to calculate the second order derivative of this system because zygote is doing that for us. We write a function that is the differential equation model, and then we write another function, which I would just add a prime on top of this function, and it is the second order derivative. And so that is one plot that we can do for a one population model that tells us we have two equilibriums. So we have about 5 more minutes, and I don't really want to start a new example that is going to be taking a little more time than 5 minutes. So I suggest that we break here and we take 15 minutes of break. We come back here at 10 past 10. We are going to have another look at a single population model, which is the Alley-Bowen model. And when this is done, we will move on to a two population model, talk about isoclines and talk about vector fields, and see how we can take this same reasoning and put it in a two-dimensional place for a two population models. So let's take a quick break, 15 minutes, and I will see you at 10:10.